Fast. So let me start by revising some of the things. So we have observed that if X is any set on which we have defined the topology, X is a set on which we have a topology, then any subset of X I choose, I can define a topology on Y, and whatever Y is given, depending on that, I will take the intersection of all open sets in X, and the corresponding topology I will get, the corresponding collection of sets I will get U intersection Y. That collection is denoted by tau Y. So depending on which subset of X I am taking, I will get a collection of sets tau Y, and we have verified that it is a topology, and this topology is known as the subspace topology on Y. So basically these are the open sets with respect to the subspace topology on Y. U intersection Y is a open set when U is open set in X. Open set with respect to the topology on X. So this is about open sets, and then we discuss one result regarding closed sets. So if Y is a subset of X and on which I define that this topology, subspace topology, then what are the closed subset of Y? That means basically what are the closed sets which are subsets of Y? So we already know closed sets of X, but now I am asking closed sets subsets of Y. So since all the open subsets of Y are of the form U intersection Y, using that fact, we can derive that all the closed subset of Y is always of this form, C intersection Y, where C is closed in X. So this result says that if I know all the closed subset of X, that means I know all C, all the choices of C, then I will get all the choices of A, right? If I know C, then I already know Y, so C intersection Y will be closed in the subspace topology. And on the other hand, if I know any set A is closed in Y, then it is always of the form C intersection Y for some closed set C in X. So that is this theorem if and only if. So in the previous lecture, we discussed the definition of interior. So interior is the union of the sets U, such that U is a open set, which is a subset of A, and U is open. U is open and it is contained in A. So by definition, A interior is always a subset of A, because what we are defining A interior is we are taking all U which contains A, which is contained in A, and we are taking its union. So union also is contained in A because of this property. The same way we have defined the closure. So closure is the intersection of all set W which is closed in Y, and it is contains A. So basically it is bigger than A. It contains more elements than A. So again, by definition, we know that a closure always contained A. So we already know this from the real analysis also, that closure of a set always contains the set, because a closure is basically A union the set of limit points, right? So A is always there. Now, what is the difference here is now I have two topological space. One is X and the other is Y. So one is X and other is Y. Y is a subspace of X. So that means I can define closure with respect to X. So uh, that is basically intersection of all the sets which contains A and W is closed. Closed in X means closed subset of X. And I should write subset of X. And on the other hand, if I define closure in Y, the same set, so what is A? A is a subset of Y I am considering. So for any subset of Y, this is definition of closure of A in X, this is definition of closure of A in Y. So let us say some other notation we can use. We can use W also, it doesn't matter. Subset of Y now because I am taking closure in Y. So now we know that every closed set in the subspace topology on Y is of the form intersection. So it is basically this V is of the form the intersection Y always, because every closed set in Y is always of the form C intersection Y, where this C intersection Y contains A and C intersection Y is closed, any closed subset of Y. So basically here we are saying C is a closed subset of X. Okay, this means this, if and only if. So now we know C, using this definition of A closure Y, can we prove this result? So this result says that we need to show that A closure Y is A closure intersection X intersection Y, where this is nothing but closure of A in X. So usually closure of A in X we denote by A closure simply. So now I have to prove this, I have to show this is subset of this and on the other hand. So we already know A closure is closed in X and uh, because it is an intersection of the closed set and intersection of, arbitrary intersection of closed set is closed. So A closure is always closed by definition and therefore any closed set intersection Y is closed in Y. So A closure intersection Y is closed in Y. Now by definition what we discussed just now of A closure Y, uh, we know that this set always contains A because A is a subset of Y and A is a subset of A closure. So A is always subset of A closure intersection Y. And therefore, now once any set contains this set, this is a closed set which contains A. And what is A closure? It is the smallest set which is closed and contained in a closure. It contains A. So therefore we get this condition by the definition of A closure in Y. And on the other hand, this set is always closed in by the definition of a closure in Y. So therefore, and any closed subset of Y is of this form, D intersection Y, where D is a closed subset of X. So therefore, and on the other hand, we always get A is a subset of A closure Y by the definition of closure, and these two sets are equal, therefore these two are equal. So finally, we get A is a subset of D because A is a subset of D intersection Y. Right? We already know D intersection Y is subset of D. So therefore, using this, we will get A is subset of D, and what is A and D? A and D both are subset of X. So now I can take closure in X. So A closure is contained in D closure, and D closure is D because D is closed. D is a closed subset of X. So therefore, closure of D in X is same as D. So therefore, we get A closure is contained in D, and the final punchline is that if A closure is contained in D, then A closure intersection Y is contained in D closure intersection Y. D intersection Y is equal to A closure Y. So therefore, we get the other inclusion that A closure intersection Y is a subset of A closure Y. So basically, we are we use here only the meaning of the pro subset of the subspace topology, and the other fact is A is contained in A closure. So these two things mainly we use for this theorem. So now let us see some example which we can uh, to understand this theorem, where we can apply this theorem. So let me take a particular subset, uh, open 0 to closed 1, which is a subset of R. So basically I'm taking here X equal to R real line, and let us take some subset of Y. So I will take A to be the set open 0 to 1 by 2. So then what is A closure? A closure means closure of A in X. So X is the real line here. So I have not mentioned, but here on R we have standard topology defined. So with respect to the standard topology, what is the closure of this set?
Close 0 comma half.
Yeah, it is the closed interval 0 to 1 by 2, because basically we have, for the closure we know it, we have to take A union the set of limit points. And limit points, there are only 0 and 1 by 2 are the limit points other than the points of A. So therefore A union the limit points contains only two extra points, 0 and 1 by 2, other than points of A. So therefore this is closure in real line. So now I want to find
Sir, if you go by the definition, then means intersection of W all.
That also we can use. So that is also possible. Did I discuss that in the last lecture? I think we discussed this thing, but this we discussed for the standard topology, right? So what is your question?
Yeah, fine. Sir, I'm saying that if you go by the definition, means intersection of all omegas, then it is going to be same answer, but different
Yeah, so
procedure.
that example we already discussed in the last lecture,
Yeah, yes, sir, fine.
right? But if you are asking for the subspace, then that we did not discuss in the any example, but this theorem we discussed. So the closure in the subspace topology you can find using this definition for every subset A using this intersection definition, right? But for that you have to check for every kind of C intersection Y, all possible choices of C intersection Y. First you have to find, and then you have to take intersection of all those sets. So it takes some time to find all such sets. It is not hard, but it takes some time. So you can try it as an exercise, and then you will come across this theorem. If you use this theorem, then you have to just find a closure, because then you know y. So if you know a closure, you just take intersection with y, you will get what is a closure in y. So that is what we are going to do now. So a closure in y is what? Basically, from theorem, it is a closure intersection y by the previous theorem. And now we can use this. So what is a closure in y? That is the intersection of closed interval 1 by 2 with y. Y is open interval 0 to open close interval 0 to 1. So intersection is open 0 to closed 1, closed 1 by 2. Right? So this is basically how to find a closure in y. So now can you tell me, if I take another example, I take y is open 0 to closed 1. So can you give some example of closed sets in y?
G singleton 0.5.
0.5. Why it is closed?
If we take complement with respect to y, then that complement will be open in y. Hence it is
Right.
closed.
So other way to say the same thing is it is intersection of these and this is closed in X. So therefore this is closed in Y. So what about this side? Is it closed in Y? Can I write it as some closed set in X intersection Y?
I think not possible.
What about this interval?
Yeah, possible.
Right, so this set is closed in Y. Similarly, this set also you can write as right. So this way you can find all the closed subset in the subspace topology, and then you take the find all the closed. So these are the closed sets. Now you find all closed sets. You have to take all possible intersections of these sets, arbitrary intersection, and all finite union of such sets, right? Because closed sets are closed with respect to finite union and arbitrary intersection. Using these sets, you can find some more closed sets. So for example, this set is also closed in Y because this is closed, this is also closed. So this way you can find all the closed sets, and then you can use the intersection definition, and you can find the all such sets containing the given set A, and then you take all intersection, you will find A closure Y. So this process is a bit difficult. So therefore that using that theorem is a bit easy because finding closure in A is easy because we know the standard topology. So this will answer the question of Vikas. So now let me go to the next notion. So A and B are two sets. It may be subset of X or any set. We say that A intersects the set B if A intersection B is a non-empty set. So for two sets, there are two possibilities. Either they intersect or they does not intersect. They does not intersect means they have no common point. So this situation is A and B intersect. So intersect means there is some X which is in both the sets, and here there is no X. So there is no X means they are disjoint. And not disjoint means they intersect. They have some point which belongs to the intersection B. There is some point in X which is both in A and B. So this concept is useful in the for the closure of a set and limit points. So let A be a subset of the topological space X. Then the following statement holds. First statement is that X is in a closure if and only if every open set U containing X. So every open set U which contains X, its intersect with A is non-empty. So this we will prove, and the second statement is that X is in a closure when only if every basis element B containing X intersects A. So let us try to prove these results. So first statement, we want to prove that X is in a closure if and only if every open set containing X intersects A. So we will prove this by using negation of this statement. So let me write down the negation. Negation is that X does not belongs to a closure if and only if there exists open set U containing X such that U and A are disjoint. So if they does not intersect, that means they are disjoint. So that we have already discussed using the Venn diagram. So let us try to prove this. So let X does not belongs to a closure. So a closure is a closed set. By the definition, it is a in the arbitrary intersection of closed set. So it is closed set. Therefore, its complement is open set. And X is not in a closure. That means it is in the complement. So what I need is I want to show that X belongs to some open set whose intersection with A is null set. Now from this step I got a open set. So what I need to check, if I can check its intersection with A is pi, its intersection with A is pi, then I am done. So let us define U to be the X minus a closure. So what do we know about U intersection A? So U is this side, intersection A. So what will be this intersection?
I think, sir, a complement A intersect phi phi
Why? Why?
because it inter
A
x
is
intersection A bar complement होगा.
so A is always a subset of A closure, and we are taking complement of A closure. So A closure intersection is closure complement is always a null set. So these two things we are using. And we already know X belongs to U because X belongs to this set. Therefore, we are done with uh, which direction? The forward direction. Now, conversely, what is given? Given is that open set U which contains X sorry small x so that its intersection with A U intersection A sorry is pi. So I want to show X does not belongs to A closure, that is we want to prove. So now what we know is U is open. So if I take the complement of U, then complement of U is closed set. So therefore X minus U is closed, and since U intersection A is pi, you further know that A is a subset of X minus U, right? U and A are disjoint sets. So therefore A is contained in the complement of U. This is complement of U, all these points. So A is a subset of the complement of U. And what we know is X minus U is closed. So if I take from these, if I take closure, then A closure, since A is contained in X minus U, this is contained in X minus U closure, but X minus U is closed. So X minus U closure is X minus U. So now what can we say? Can we say X does not belongs to A closure? So how does this follows? So X is the element of U and A closure is a contained in the complement of U. So if X is in U, it cannot be in the complement. X cannot be in the complement. If X is not in the complement, it cannot be in the subset of the complement. That is we use here that X does not belongs to the A closure. So this is the first part which we proved the converse of this forward direction. So A part is done. Now what about B part? So if I know that A follows, then can I prove using A the part B? So first part says that X is in A closure, then every open set intersects A. So if every open set intersects A, can I say every basis intersects A?
Yes, because bases are the collection of open sets. If open sets are doing, then basis of course will do.
Will do because every basis element is open set. Right, therefore it is known as basic open sets. All basis elements are known as basic open sets. So every basis element is open. So therefore, using this implication follows. Now, what about the converse? So to go converse, first I have to go from here to here. Then I can use the converse of this part. So if I know every basis element containing X intersects A, do it follows that every open set containing X intersects A?
Yes, sir. Yes, sir. Sure. Because this is also open source.
Basis open set we used first time. Let me write down this. So X is in a closure. It gives for every open set. This implies for every open set U containing X, U intersects A. That is this first part. And now I know it intersects. So therefore, take U equal to B, where B is a basis element. Containing X. So this implies every open set. So in particular, take U equal to B, where B is a basis element of X. So therefore, in particular, what I will get, this statement becomes, therefore, for each basis element B containing X, B intersects A. So this is forward direction. Now what about the converse direction? Converse direction is that for each basis element B containing X, I know that B intersects section A is null set. So this notes is over. Let me go to the next slide, next page. So does this follow that every open set containing X intersects A? So what I want to say is every basis element is open, but every open set is not basis. So conversely, I cannot use that fact. So for converse, I have to use some other thing. How can I go from here to here? So how to go from open set to basis? So if X belongs to U, then how do I get basis? Can I get a basis element?
It will be basis element if you satisfy the basis property that.
Yeah. So the which property we can use? The first property, right?
Yes.
So by the definition of basis, there exists a basis element B such that X belongs to B, which is contained in U. And then we can use this property that every basis element contain X, the intersection is null set. So since the intersection A is non-empty, implies U intersection A is non-empty. Why? Because B is a subset of U. So if X is element of U, I can always find B so that B intersection A is non-empty. So if B intersection A is non-empty, obviously U intersection A is non-empty. So this will complete the B part of this theorem. And so I thought I will be able to cover limit points today, but there is not much time. So let me stop here.